Hello. Testing. Cool. Believe we are working. Do we have people? I want to double check that everything's working, so if someone can comment, that would be appreciated. So right now I'm just doing the tests because I happen to know that there will be a lot of very difficult cases to hit. So here I'm testing overflow. So yeah, this test, even if you compensate the arithmetic, you need to make sure that you do special stuff to get the right answer. Why is that gray? Oh, yeah. Cool that Visual Studio can detect that. What other tests are there? Does FMA exist for float 16? Ooh, did we just get someone? I do not users in chat. Oh, cool. Hi David and Mose and Random String. Let me know if everything's working, because I'm not 100% sure I'm seeing the chat. I guess I should figure out if I'm not seeing the chat, because if I am, or if I'm not, then you guys won't be able to see it. Or I won't be able to see you telling me that I'm not, so... Double checking stuff. Oh, cool. Echo. Give me a sec. Now I can actually see the chat. So that is good. OBS. Oh, yeah, my mic isn't quite as good as it should be. This is what I want, I believe. Properties. Sound settings. Input. Oh! How's that? That theoretically should be better. Cool. Tomorrow I have a Blue Yeti showing up for work, but that isn't here yet, so we're dealing with a mediocre webcam one. But, yeah, so basically, the goal for today's stream is to get a software implementation of FMA done. The thing that's really hard about that is that FMA computes, so FMA of A, B, C equals 8, typing is hard, times B plus C, but it needs to do that with only one rounding operation. So getting that to fully work correctly is difficult. Other tests that we should add are probably test that this float min of t, this should be inf of t. Oh, we do have a float 16 method of FMA. Let's see if I can find that, because I'm curious. Base float func. So you can't see what I'm currently doing. I'm currently looking through. Oh, so the case where the intrinsic isn't available is for x86. So for Intel, it's pre-Haswell, which is 2013. For AMD, it's pre-Bulldozer, so 2012. But then we also want to support Arch, we want to support ARM, and in the future we theoretically want to support what's it called? RISC-V. Hi, Slurp Wi-Fi, or Wafi, not sure how to pronounce that. Where is the Float 16 one? Edit, FMA. But yeah, so basically it's a bunch of platforms that we don't really care about. So this doesn't have to be incredibly performance critical, although I'll try to do a decent job. But the hard thing is just getting correctness, because we don't want to say you have to have this new of a processor to run Julia. And then also, Okay. Oh yeah, that's a dumb definition, so that we don't really need to test. That will just all fall through. But yeah, so basically this is the last function that we currently call out to C for. So by removing this, it lets us get rid of the C dependency entirely, and that will be very nice. And also, about 2 hours ago, I was bugging Jeff a little bit about actually getting the multi-versioning support that we need so that this will actually work. So yeah. Now I think we have a decent set of tests for now, so I think it's time to start actually trying to implement this in a way that passes the test. So the very first implementation is function fma at bt ct, where t is a subtype of float32 or float64, which are the two cases we care about. Actually, the float32 is easy. So let's actually do that separately. Because for float32, we just can do return float32 of float64 of a times b plus c. And I believe that should be valid. Because basically this will convert to float64, and float32 has 23 bits of precision, whereas float64 has 54. Or 53. So when you multiply two numbers, the maximum precision that it has is the number of precision of the bits added together. So this will be fully exact, and the exponent range is wide enough that we can't overflow. And then this addition also shouldn't ever round. Pretty sure. We'll try it for now and see if it works. So we'll call this my FMA for now. Yeah, because I want to be able to use base's FMA to test against. And for now, I'm going to comment this out. That was not what I meant to do. So for now, let's just do for t equals float32, and I'm going to comment this out. And let's see if this works. So one of these errored. Which one errored? Oh, the one where that's not how iterators work. Oh, this should be t of 1, and this should be t of 2, so that we actually have type stability for these tests. And this is t of inf. Typing is hard, guys. Now our problem is that, yeah, this isn't correct, because this needs to be caps of float max of t, because otherwise it's close enough that it should just round down. Cool. So our float32 version works. at least moderately well. It wouldn't shock. I don't think this has any bugs. So now onto the Float 64 version, which is the actual hard part. Also, if any of you have any questions about anything I'm doing, please ask. Because a lot of this stuff, especially what's going to be coming up, is going to be pseudo or somewhat black magic-y. Okay, so first thing we want to do is compute a times b equals a times b. Then we can get the low part of a times b equals FMA. Oh, yeah, I forgot. You can't. Yeah, so this is why it's hard, because the regular way that you would get the error of a times b would be FMA of a negative a b, or ab, or a negative b, ab. So, but then the problem is that we don't have FMA hardware, so we can't do this. And this is where our problems start. So what we have to do instead is do some magic to break A and B into their high and low bits so that we can multiply them exactly. And this is going to be very difficult, which is why I haven't done it yet. So, function split bits, x is going to be a float 64, so x high equals x minus x times. Hi, Brain RPG. Nice to have you here. 2 to the negative. What's 53 divided by 2? So 27, I think, is what I want. Or 26. Because, yeah, there's an implicit bit that you get for free. I believe in Julia to constant fold this, I think. Yeah, so basically what this is doing, x low equals x minus x high. Return x high, x low. Oh, yeah, I can do that. Yes, I have more screen real estate than you guys see because I'm using a bigger monitor and I've set stuff up differently. But yeah, no, that is much better. Good suggestion. Yeah, so the idea behind this bit of code is that this will round x down. So this is a very, very small number. Is this right? What I want to do is zero out the low bits of x. Let's try it. That is a much smarter idea. Let's mask out the low bits instead. So, reinterpret float 64, reinterpret uint 64 of x. And then I want to AND that with OX. So I want to leave 26 bits, we said. So 26 bits is FF is 8, FF is 16, FF is 24, plus a 3 should be 26. And so then we need 1, 2, 3, 4 is 2 bits, 4 bits, 6 bits, and yeah, that should be correct. Yeah, does it need the space around the and? It should do exactly the same thing. So let's try this. Split bits 1.1. I screwed up my F's and my zeros, so this should in fact be wait, is it a tilde in Julia? Yeah, it's a tilde, I think. Yeah, this is the actual magic number that I want. That looks promising. So, reinterpret 1. uint 1.1, and so reinterpret this. So that is, yep, 4, 8, 12, 16, 20, 24, 25, 26 bits of zeros. That's perfect. Okay. So now what we want to do is A high, comma, A low equals split bits A. And then we want to do the same thing for B. Yeah, there is that. But the thing here is I want half of the significant, a significant, not the whole significant, so I think I just need to write it myself. So then what we want is AB low is A high times B low plus A low times B high plus A low times B low. Should be correct. This isn't. So those exact. I might have to look up. There's a formula to do this correctly. So Julia FMA native is wonderful for everything, or for the processors that have a native FMA instruction. But currently we are calling out to OpenLibM because not all processors have a native FMA instruction, and so for the ones that don't, we need to emulate it. Hi, Yingbo. We're making some progress. If anyone wants to find me the canonical way of writing the error-compensated A times B, if you don't have FMA, I would appreciate it, because I don't feel like doing that on stream, but I will probably spend 20 minutes banging my head against this wall otherwise. But AB high equals A high times, come on, B high. I'm going to change these names because I have just misspelled them 6 times, which suggests that they're bad names. This all looks correct, although A-low times B-low should be first in this list, I think. Although, actually, it might not matter. So the reason why writing FMA and Julia won't result in emulation is because I've been bugging Jeff for the past couple months to get us multi-versioning for this. So the final way that this is going to work is Jeff is going to put something that's like if native FMA equals like blah 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 processor intrinsic. Else FMA equals emulated. And so the idea is that this will compile down to a constant, and then everything will work. Yeah. It's going to be slightly bad, but with a little bit of luck, I won't have to write that. By which I mean, I'm not going to be the one who writes that. So hopefully I can bug Jeff into doing it, which I think I'm going to succeed in doing, because I sit across from him at work. But I believe this is correct. Dropping dependencies is great. Basically, the fewer dependencies we have, the faster everything builds, and the smaller everything is, and also then we get the bragging rights of saying, yeah, all the math is Julia only, and that is worth something, at least to me. So now what we want to do is do AB low plus C. That probably does round. AB low PC equals that, and then AB low PC low equals. So I think we can assume that this is smaller than C. Let's not. Something I want to find in trig.jl. Where is this? Somewhere we add 2 con h. This is a fast way that you can add 2 numbers. I'm going to steal this. And the reason I'm going to steal it rather than re-implementing it is because we don't have a y-low in this case. So we can say this. So this is plus C, and this is AB high. I want this here, in fact. And then greater than C, AB high minus R plus C plus 0 plus AB low, and here it's C minus R plus AB high plus AB low plus Y silo. Are these the same? No, they are not. They are close to the same. I think this may be correct. So this deals with everything other than the overflow checking so far. So let's try running the tests. My guess is we're gonna have 2 passes, 1 fail of the float64 code. Let's find out. Everything passed. That was not what was supposed to happen. Let's try running again with the actual... Yeah, perfect. So, yeah, as you can see... Oh, yeah, I also need to test FMAs with everything. So let's see, FMA... REPL window is off-center. What do you mean? Oh, yeah, you can't actually see all of my REPL. Let's fix that. Is this cropped? Oh, yeah, now you can see all of it. Discard. Oh, wait. Is that not actually... Okay. I believe this is... This good? I think it should be good. Inf1 negative inf nan. Okay. Inf01 is nan. Okay. Oh, wait, I need to use... Okay. Those all are nans. That's kind of expected. Any other weird cases I need to think of? Okay. Test my FMA inf e of 1. What were the others of those that I was surprised by? None of those are too surprising. If there are other edge cases I'm not thinking of, would appreciate them going in chat, but yeah, there's a lot of possible edge cases for stuff like this. So we're going to be finding those over time, I'm guessing. Wait. No, this is bad. Nan should triple equal Nan. Yeah. Why is this test failing? Oh. Yeah, there are different Nans. Let's play. Which Nan is this? The decision to have multiple Nans is one of those decisions that IEEE just totally got wrong. Yeah. Okay. I believe math.jl actually has a fix for this because we don't actually care what Nan it is. Because Julia in general does not guarantee you the correct Nan. Yeah. Oh yeah, so cool. Now we're only failing this one test, which is going to take us a while. So what we want to say now, is if AB high equals inf, then we need to rethink our life choices. And actually what we care about is abs of this. And then we also care about, so then if, do we have sine? Yeah, branching's unavoidable. In general, emulating FMA takes like 100 cycles to emulate a one-cycle instruction because there's so many different possible edge cases. My guess is we probably won't catch all of them tonight, and someone's going to make an issue on 1.8 saying that, hey, we missed something. So, if sine of C equals sine of AB high, so if, actually what we want is, if this, or AB high equals 0, this testing will have to grow significantly, I believe, to actually encompass everything that we care about. That said, these are a type of tests that are hard to do for CI because, actually, we can do some randomized testing using big floats. That won't be too bad. Return think we can actually do this a little more efficiently. So sine AB equals this. And then we can do that in time. And I think this might be correct. And then, else we have to do some really complicated stuff. Oh yeah, OpenLibM was basically us getting annoyed that all the libm's are broken and making our own. So, what we need to do here is return we need an algebraic identity that fixes everything. So I think what we want is A times B plus C equals A times B plus C over B is valid. So then we have to compute that, and that's awful. Okay. So to compute this, we just have to go for it. So I need division here. That is... Can anyone figure out a way to rescue me from having to do what I'm about to be doing? No, so hardware implementations of FMA don't branch. Hardware implementation of FMA, they just use more bits in hardware on the APU, and then everything just works beautifully. But no, in software we have to do some really slow branches. That said, I'm also not a hardware engineer, so take anything I say about hardware with a grain of salt. But no, hardware does not branch. FMA in hardware is a 0.5 clock cycle bandwidth and 4 cycle latency, I think. It's basically the same as addition. At least on newer processors. On some of Bulldozer, I think, and even Zen 1 didn't have great FMA instructions, but it's still much better than having to do it in software. So now I really want to find a less horrible version than this, because this is not going to be cheap to compute because it uses a division that I have to compensate. But I don't really see an alternative. So... I might just have to do this. Is there another identity to use? I think no. So COB equals C over B. Wait. Is there something? I would very much like something. Try Herbie. That is a good idea. Herbie... can you link me to Herbie? I don't have it. Like, I know you can use it on the website, and I don't have it downloaded, so... Okay, I found Herbie. This is going to be off stream because I don't feel like finding it. Web demo. A times B plus C. Thank you. Okay, Herbie's coming. Herbie's very useful here. Herbie says, use FMA. I'm not happy with that. Oh, also, I like how my stream setup gets screwed up when I go to a light mode website. That's funny. Maybe there's an advanced options. Nope. At least not in the web demo. If one of you wants to figure out, I think what I'm gonna do is, just do this and it won't be accurate, and then someone else can hopefully find a version that actually, figure out how to coerce Herbie into not giving back FMA. But let's try this for now. This might pass the test. No, it does not. What is wrong here? Wait, this should be C over A. That's what's wrong here. Cool, that passes. So now we need to try the worse edge cases. So now we can try next float P of 1. Oh wait, this can't go in the loop. It's going to be different. Yep, so that's a broken test case. And I should probably copy in the right answer. This isn't even subnormals yet. I'm sure there will be bugs with subnormals too, but we are not at that stage. So now if we run this test set, I expect to see one failure. Yep. Are there any subnormal failures I should be worried about? I can't think of any. But that doesn't mean that there aren't any. You know, there's a really dumb way we could solve this. This is a valid emulation. I don't feel good about it, but that will work. So the problem with running a full loop on float 32s is because it's a 3-input function. There's 2 to the 32 times 3 possible. Yeah, there's 10 to the 28 possible 32-bit values, so that's not achievable. And the other thing is, even if it was, most of the bugs come from places where you have low bit set, so honestly, you aren't going to do much better than some strategic randomized testing once we fix all of the current bugs. But wait, what? Did I not copy and paste this in yet? Yeah, Smart Fuzzer would be lovely. What the? Is it just me, or have I found a bug in floating point hardware? Did I copy my test? Wait, is that 5 volts? I bet this is only 1 ohm, but let's find out. By the way, this is a... Yeah, okay, yeah, that's only 1 ohm. That is... I think that's still a bug. Yeah, this is a package I wrote. I hope no one's using it, because it is not really documented or stable. But basically, it provides iterators over floating point values. And also it provides a set of functions to test the accuracy of mainly one-argument functions. It was pulled together based off of code given to me by Chris Elrod, which was given to him by Mose, I want to say, but I'm not sure about that. So, yeah. How do you set precision of big floats? Set precision... let's get precision. Okay. So, is this a bug in floating point hardware? I think it is. At least I don't know what else it could possibly be. Oh, there is one other thing it could be. This one? No, it was this. Wait, what? What's happening here? Something is very strange. What do you mean by dynamic precision range? Oh! What? This is an exact floating point value? Okay. No, no! That can't be right. This is too many bits. What the hell is happening here? Like, big point 1. Oh, okay. Yeah, it can't have extra bits. But no, yeah, this is a reasonable number of bits. You can have, yeah, because that's gonna have 55 digits, which is, yeah. No, I didn't want the string. But, like, this is too long to be the decimal representation of a float 64, right? Like, if I divide this by 2 to, or multiply by 2 to the negative 15, yeah, no, but float 64s are exact. Float 64s have 52 binary digits, and each binary digit can add at most one decimal digit, right? I feel like I'm missing something, but I don't know what. Well, first of all, if I'm doing this, I can just do big A times big. Yeah, I don't actually have to do the smart thing if I'm going to big anyways. Let's see if this fixes it. No, that still doesn't fix it. Something is very odd. What's the maximal big float? No, because so that's not what's happening. because these are different float 64 values, which means that big float should have plenty of precision to represent them, right? I don't think type max big float, max big float, that works. Oh, okay. Yeah, no, that's way bigger than what we're dealing with. Something is seriously borked. If we look at EPS of this... Oh, yeah, that's still a really big number. Yeah, because this minus 2,000. So, the thing that I'm very confused about is big float appears to be giving a different answer than the hardware. So if we take, because yeah, this is the answer with big float, which if we turn to float 64 is this. Whereas if we go with FMA, we get the same thing now. What? Oh, did I just copy the wrong value and then not realize it for a really long time? I'd feel very stupid if that was the case. No? Yeah, so that's... Yeah, so this is the problem. Oh, what, the value's off screen? Line 14. Oh, okay. Oop. Moving me for a second. You don't need that much of me anyways. But, yeah, going back to the test. So, basically the problem... Oh. Wait. Yeah, we did get the high. So that's getting hit. Oh, okay. We aren't getting the high. So... Okay, existential crisis averted. Oh. That abs is not supposed to be there. That's a lot of the issue. Oh. Really? Oh. This is evil. No, we should just be able to deal with this here. So, what's happening is this code is going wrong. I feel a lot less confused now, so that's probably a bad sign. Typing is hard. There we go. I'm going to divide this by 2. Cool. So now I have to remember that I'm doing... If I'm very confused by what's happening, remind me that everything I'm doing has to be divided by 2 so that I don't overflow to inf. So, and then abs high over 2 plus abs low. Okay, that is all correct so far. So the error compensation works. So then I want to do C here is negative. So this is exact. Although in general it won't be. And then AB high minus R. Let's go back to the math thing that I stole this from. And I can take advantage of y low is 0 for both of these. Oh, do I need to normalize AB high and AB low? That's definitely possible. And the way to find that out is to check f's of this. Yeah, so the problem here is that AB low is too big, because this gives you two numbers that sign to the right thing, but they don't actually they aren't, AB low isn't as small as it could be. So the solution there is equals AB high plus AB low, and then I need to change AB high's name here. AB low equals AB high temp minus AB high minus AB low. I believe that should be an accurate error summation. And then everything failed. I should probably plus AB low. Which means these need to go up here. And this should just be this. Down to 2 fails. That's 1. Really? I worked so hard on this. What's the problem? Anyone want to tell me what the problem is? Oh. This should be this, I believe. No? Oh. I probably shouldn't subtract AB low off of that, maybe. Is that it? Yes. Cool. We have successfully renormalized. So now we have two options to go for, and I kind of want people to let me know which they'd prefer. Option number one is we could try to improve this. On the other hand, like, this is just a fallback method, so there's an argument that it might not be providing that much value, because if this is slow, like, we need a version of this that is correct, but it's not fast. Like, it doesn't need to be fast. Speaking of which, let's actually test how fast it is. Time, my FMA, 1.0, 1.0, 1.0. Oh, I should remove the printing code. That is a good idea before timing something, is remove your debug code. Now it's constant folding it, which is a good sign that it can do that even. And this is, if you aren't familiar with the ins and outs of Julia, this is a trick that you do to confuse benchmark tools enough that it doesn't constant propagate your answers. Honestly, that's pretty good. We take that. That's only 6 times slower? Wow. I was expecting it to be way worse. Let's see if it gets worse if we use nastier values. Yeah, guys, this actually makes me want to make the last branch fast. Because, like, if we test, float max d of 2, and then negative float max d. Yeah, there it's, yeah, there it's 200 times slower. So, do people want to embark with me on the journey of trying to do this? Also, like, might be a good time to take a break for a little bit and just put on, like, doing, like, ask me random stuff for whatever. I don't have a very clear idea for how this stream is going to go. I honestly didn't expect to get something that would work this well this quickly. Okay. Don't really have any wrong preference. You know, let's try to get this a little bit faster. It's not going to be fast, but we, I think, can do a bit better. So what we want to do is leave in here. I have a division that I compensate. Yes, it's right here. This is for the work I did on float 64 powers. Really I should put these into functions, but that's not happening now. So where was I? I was here. So MP1 high in this case is going to be A. MP1 low is going to be 0. Makes this easier. That makes it much easier, because that gets rid of this FMA entirely. What was M here? M minus 1.0 was what we are dividing by. Which in this, or what we're dividing, which is C. What's X high? Is that? Oh wow! I thought that this was worse than it is. Yeah, so this is going to be AOC yeah, so this is A divided by C high and AOC low. And this is going to be inv A. Oh, no, we have a problem. Houston, we have a significant problem. This is another case where we error compensate with FMA. Abort. So, right, now we have to do this dance again. Honestly, I'll put into a function. So this is going to be function 2mol x float 64 y float 64 so these should both be in line. AB high, AB low equals 2mol AB. Why am I changing this? A and B are perfectly reasonable variable names. So yeah. amazing how we need to fractally implement FMA in order to implement FMA? Oh, wait, we can do something really dumb here. We can recurse. Because this will always be a fast case of the algorithm. And then what we want to do is add b and then multiply by a. That's not that bad. We are almost out of the woods on this. And I believe we know that b is bigger than c over a, at least in magnitude, because either b is big or can't see after line 42. How's this? I need to make this all work a little better. I think part of the problem is that I upgraded my monitor, so now all the pixel counts are screwed up. Thank you for the warning, but yeah, so this should be better. But yeah, can someone confirm for me that because either A is big or B is big, because we got here, it's reasonable to assume that B is bigger than C over A? I think that's the case. I'm gonna go for it. So AOC PB I equals AOC plus B, and B is exact. Is this valid? Right, and then I can say the low part equals, that is true, so I want this version. B minus AOCPB high plus C is plus AOC high plus AB low. AB low is AOC low. Right? Yes. So now we just need to multiply this by A. Oh, and this is easy. This is just AOCPB high times A res high equals that, and then res low. Or wait, no, this is just 2 mole, yeah. No. Yes. 2 mole of this. And then for the magic trick, we should just be able to return res high plus res low plus a times this. Anyone want to take bets on whether this works? It very much does not work. It would probably work better if I actually defined all of the stuff I'm using. That still doesn't work. Attempting to access float 64 at index 2. I was not expecting that error. What the hell? Anyone want to tell me what I screwed up? Return 2 things from U. What's U? From Tumul. Yes! Return AB high, AB low. Good catch. That is valid. And that is twice as fast as it was before. Right? I'll be honest, I thought it would be better than that. But I guess this is a recursive function. That's really slow. Wait, we broke something real bad. That's all blue. Why is this multiple times slower now? Like, way slower. Minor apologies for the pre-compilation that's about to happen. Wait, it allocated? If it allocated, that's the problem, because this really shouldn't allocate. Yeah, that allocates. That's bad. Yeah. can confirm 8 allocations. And how many bits was it? It was 144. Wait. The number of allocations is dependent on the values? That seems a little weird to me. Are we allocating the tuples? That really shouldn't be happening. Theoretically, we'll have a, profiling up soon, which should show where it's happening. But something is very odd. Also, just wondering, Martha Ford, are you, like, on, Discourse with a different username? Just don't recognize that username, and you're being helpful enough that I feel like I would have bumped into you before. Okay. You guys won't be able to see the results of this profiling, but I shouldn't be in it for too long. Never mind. Everything broke. Let's try restarting Julia and seeing if that fixes it. Oh, hi, Cedar Prince. We're in decent shape. We have this, which appears to work. Yeah. P equals float 64. Somehow I've managed to write a version of this that allocates, which really shouldn't be possible. So right now I'm trying to see what I screwed up. But profile view is broken. I guess I'm not going to be profiling this. Is there an easy way to check for allocations? Ooh, you have a dog. Dogs are wonderful. What is a good way of tracking allocations, guys? have code warn typed this, right? Wait. Okay. Have fun with that, pseudo prints. Tuple vote 64s. This is the issue. What is partial struct? Is this Julia being bad at optimizing recursive functions? Let's just do this to test. No? What is happening? We are way faster before, right? I'm not hallucinating this? What broke? Something is very wrong. And it's not at all obvious. We can always try b-timing tumul, which should be very fast. Oh, what? How is that 400 nanoseconds? Why is split bits allocating now when it wasn't earlier? I had code native on this. And moves, subs moves red. Wait, why is plus taking 400 nanoseconds? Something is deeply strange. What broke? Because my benchmarking is suddenly just completely screwed up. I'm pre-compiling stuff because I don't trust anything now. Oh, is this just that t isn't const? Yep. Apologies for me freaking out over nothing. That was a classic case of... yeah. This is what I actually wanted to test. That still feels wrong. That note's definitely too low. Right? Yes. Oh, it is returning the wrong result, which is at least a bit of a good sign. Oh, that's part of why. That looks a lot better. Okay, so we are 25 times slower or so? And if we take the non this case, so let's say b of 5, that's just straight up respectable. Yeah, okay. So really? That seems a little hard to believe. This is more than 3 cycles of work. Y64 equals FMA x64, x64, x64. Okay, that's more believable. Okay, so for more realistic use cases, we're 9 times slower. That's still pretty good. Especially because I think the current state of the art with Julia emulating FMA for libm. Actually, let's find out. How do you set the is there anyone remember what the magic command is? So we want, let's call it SSE2. Or is Sandy an option? It's not Haswell. Ivy Bridge. Oh, I'm built for a March native. Oh yeah, Julia has a lot of backends. It turns out that if you generate the wrong code, if you generate code for people that you don't have backends for, then just everyone's very sad at you. So I'm actually not going to test this because it would require me recompiling Julia with different architecture options, because I don't have a version of Julia, like I build from source. Also the other answer on it being a lot of backends is that I think we're just stealing them from LLVM. That, like, we might be able to do better than LLVM in some cases, but LLVM gives us way more systems that we support natively. So, now all we need to do... Ooh, any progress on that? That's cool. Oh, okay. At the beginning here, I guess it's gonna go up here. And I should probably, where T is in the union of float 16, float 32. And then this is going to be widen, this is going to be T. Cool. Oh yeah, I'm really excited to see new Paths Manager in Julia. We're theoretically hoping to get it in 1.8, but given that it's LLVM features which are really complicated, I'll believe it when I see it. But like, Rust is, seeing like a 20% drop in compile time, I think, and we would very much like that. I am very much rooting for you. Let's try to build this. Oh, but now we need to do this. My FMA with FMA. Yeah, it is. And then these tests go in base.math.jl. And they'll go at the bottom. And now it's time to make Julia and see if it works. Minor apologies if the stream breaks. I'm making Julia with 5 threads because I want it to complete faster. I think I have enough CPU to deal with that. But if stuff lags out, now you know why. This is gonna take a little bit. Also, I probably should have commented out the float funcs part of this. Yeah, so I got into Julia. So one of my parents' friends, who's a biology and ecology teacher at um, University of Vermont, told me about Julia when I was like late in high school, I think, so like senior year of high school, and then I didn't really play around with it much. Oh, so Brain RPG, yeah, I think you're right. About the profile picture, because basically I just used a generic profile picture until this year, basically, and then I switched it to the airplane in an Eclipse one, which is actually one that David, who I believe might be in the stream still, he was at some point, actually took, and that's airplane in a solar eclipse. But basically, yeah, so then I played with Julia a little bit in college, and then like COVID hit, and I was bored. And I was talking in I was talking in Discord with someone about how our exponential functions were kind of slow, and so Chris Elrod basically showed me how to do some stuff and like gave me an algorithm description of how glibc does it, and basically I started working on a copycat implementation that would be safe there. And yeah, then that progressed a bunch, and I got that merged, and then I just found I really liked doing the low-level math stuff in Julia, so I did that for until now. So, kind of long story, but there it is. So, now we are almost compiled. So yeah, this is the part that Jeff's gonna have to fix at some point. But it lets us remove FMA libm, which, you know, is cool. Yeah, I am planning on writing a series of blogs for this, for the floating point stuff. Some of it's just that it's really low level, so there's some limited amount of interest, but some of it, like, we could use an extra 2 or 3 people working on this, both in base and also special functions, could use some love, which I haven't done anything with yet because I've still been working on fixing all of the things in base. Come on, Julia, finish up recompiling. You're almost done. Oh, cool. It's actually, it built successfully, so that's a good sign. Then the only thing we need to do is check that it actually works. And then we can make pull requests. And I'll probably end the stream with that. Okay. Yeah, that didn't work. Don't know why that didn't work. Oh, Yep. I included this in the wrong spot. Okay. I think I'm probably just going to end the stream now. We've been going for 2 hours, and I think we've done what we wanted to do. So glad that you could drop by, Peter Prince. Yeah, the goal of these streams is to make it so that I actually bother doing this stuff, and B, hopefully teach people a little bit about the lower level floating point thing. So if you learned something, that's great. Final perf percent, if I remember, let's actually just test it now. So yeah. The VOD's gonna stay up on Twitch for a bit. I'm probably not gonna bother to throw it up on YouTube because that would require effort. But Twitch has 30-day limit. Wait, no, I already got this in base.math.fma. Oh, okay. Then I will export it to YouTube probably, I guess. And then if we do base.math.fma. So yeah, for random values, it is, I believe it was somewhere around 9 times slower, but let's actually get a precise figure. Yeah, 9 times slower, and it's more than that for large numbers. So yeah, this branch is even slower because it has to do a recursion step. So that's going to be 18 times slower, let's call it. Maybe a tiny bit more. Yeah, so I think it was 30-ish times slower that we saw for this branch. But honestly, I'll take that. Because before, I believe the libm one... Oh wait, I can actually test this. Base dot... libm... FMA. Is this what it's called? No, it is not. Base dot FMA libm. So yeah, let's see FMA libm, which is what currently yeah. So that's 33 microseconds compared to 3. So yeah, so this is a 10% or like a 10x speed up over what we were using before when you needed to emulate it. But really, the answer is that the performance here doesn't matter especially much because if you need this, you're on a slow processor anyways. So yeah, with that, I'm going to end the stream, I think. So glad all of you were around. I'll do something like this at some point in the future. Yeah, bye. Now can I figure out how to...